So cosets of a subgroup. So 7a, for n greater than 1, describe the left cosets and the right cosets of the alternating subgroup an in the symmetric group Sn. So one coset consists of the even permutations while the other coset consists of the odd permutations. Basically the left set is either the odd or even permutations and the right is the odd other type of permutation. Basically right cosets are even or odd and the left is the opposite. So if left cosets are even, right will be odd and vice versa. And you can also just kind of see that this will happen somewhat, that there will be only two distinct cosets as the index equals 2, and there's a formula for that and all that. And multiplying even or odd, permutations given even or odd permutation when checking cosets. Yeah, there's a lot, just a kind of theory one, just the idea behind what's going on. Statement more than anything. But yeah, it's the even and odd permutations that are left and right cosets of the alternating subgroup An in the symmetric group Sn. So give the left cosets and the right cosets of give the left cosets and right cosets of this cyclic, in the Z12 of problem 4i. So Z12 is modular arithmetic additive group. Z12 equals 0 to 11 with the modular symbol on it. Bar. So let H equal to the cyclic group, so it's basically you add 2, 4, 6, 8, 10 to 0, so I put the 0 at the beginning from least to greater. Because 2 plus 2 is 4 when it's modular, 4 plus 2, 6 the modulars. Eventually you get 10 plus 2, which is equal to 0. You basically do just modular arithmetic where you add 2 successively to each one. So you eventually get to the end of it. End of the cycle where it would repeat. So that's what H is equal to. This thing, 0, 2, 4, 6, 8, 10. Of course, the modular arithmetic format. And left coset is I plus H, which is equal to 1. I don't know why. 1 bar plus H, the modular arithmetic to H. So just add 1 to each subzine, and you get 1, 3, 5, 7, 9, 11. And 3 plus H will also give you 3. It will give you 3, 5, 7, 9, 11, 1. Basically, so you get 1 plus 8. So basically, that's that's one set that basically is half of them all. Half of all the possibilities will give you that, and that's the left coset. And the right coset, we wrote this, yeah. Basically, I wrote it as so it's all these will be the same coset, these 6 ones. And then 2 plus H is 2, 4, 6, 8, 10, 11, 0 because of the modular addition of 2 to each one. So that's equal to 4 plus H, 6 plus, and so on. 0 plus H even. So all left cosets are 0, 2, 4, 6, 8, 10, and 1. Oh yeah, and also the right. As a modular arithmetic additive group is commutative. That's like one reason. You can just say like it's commutative. Like the group itself is commutative, so the left and right cosets will be the same when you add them. So these are the left and right cosets: 0, 2, 4, 6, 8, 10 that set, and 1, 3, 5, 7, 9, 11. The separate sets, those two sets. Yeah, and I even show an example here. H plus 1 will give you the same exact results as 1 plus H. And H plus 2 is the same thing as 2 plus H. So left and right are the same. Show that a group G of order 27 is either cyclic or such that G to the 9th equals E for all G and G. Get generalized on this and problem 9. So we have to generalize, make a general formula, which you would not be expected to be able to do because this one's not an obvious one. It's not like an obvious formula, but we'll do that in the next. We'll do that real quick after this. So the Lagrange theorem gives that G is in G, implies that order G divides order big G, lowercase g, divides order G equals 27, and order G is 27. So order G is in 1, 3, 9, 27, which are positive divised with 27. If order of the little g is equal to 27, that means G is a cyclic group of order 27, just, which is equal to G. So G is cyclic. If order G equals 9, that means G to the 9th equals E, and that's what we have to show for all these. If order G equals 3, G cubed equals E, which means that G to the 9th is equal to G cubed times G cubed times G cubed, which is equal to E times E times E, which equals E. That means that also means G to the 9th equals E. And if order of G is 1, that means G to the 1 equals E. So G to the 9th will equal E as well, because 9 G's together will all multiply 9. It'll be E times E times E 9 times. E times itself 9 times, so it's equal to E. So G to the 9th power equals E for any G is in G, in that case. Or G is cyclic, basically, for this case. The first one is G is cyclic. Finally, in problem 9.1, for this part, problem 9.1 found that a group of order 4 is cyclic or such that G squared equals E for all G is in G. In general, a group G of order P to the P power is cyclic. P is prime here. P equals prime number. So a prime number raised to a prime number, that's the group's order, is cyclic or such that G raised to the P power, which is also raised to the P minus 1 power, is equal to E for all G is in G. You'd have to really play around. I think you'd need a few more examples. You need at least 2 or 3 more group examples for this to actually make sense. These two examples aren't enough. These 2 problem types, 9.1 and this one, aren't enough. At least 1 or 2 more examples where the same thing would be applied further with maybe but regardless, but it's that's the general formula. 13.1, show that. So we have 13 and 26 now to do. So 13i, show that a cyclic group of order 22 has 1 element of order 2 and 10 elements of order 11. So G equals cyclic group A, which is equal to A2, to A22, which is equal to E. So that's a cyclic group of order 22. It has 1 element of order 2 and 10 elements of order 11. So letting G equal cyclic group of order 22, which we did. Element of order 11, that means A to the K is in G, implies that A to the K to 11 equals E, so A to 11K equals E. That means that 22 divides 11K, because 22 is the group's order, 11K is the exponent. So it means that 2 divides K here. So GCD of K and 22 equals 2. So we have from that, K is in 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Between K and 22, GCD is equal to 2. So that's 10 elements, that corresponds then to 10 elements of order 11. Because that's A to the 11, okay, A to the 11K, it's order 11, in a group of order 22. Oh, elements of order 2. AK is in G, such as so on, A to the 2K equals E you get. That means 22 divides 2K, so 11 divides K. GCD of K, 22 equals 11. K is in 11. So GCD is 11. So that means K is just in 11. So A to the 11 has order 2. So 1 element of order 2 and 10 elements of order 11. That's all you have to do for that. So finally 26, let K be a subgroup in H and let H be a subgroup in G. What are the possibilities for order of H if order K equals 6 and order G equals 288? So using Lagrange's theorem again for this one. Order of K divides order of H, so that means 6 divides order H, which implies that order H equals 6 times K. K is in Z. Okay, that gives us something for order H. H subgroup of G implies order H divides order of G. So 6K divides 288, so that means K divides 48. Simplifying it down, 6 divided by 6 and 288 divided by 6 gives you 40. So K divides 48. So K is in 1, 2, 3, 4, 6, 8, 12, 16, 24, 48, all those numbers. So order of H is equal to 6 times K, which is included in the set, times K, and K is included in that set, so it's order H is included in 6 times all these numbers, basically. So 6, 12, 18, 24, 36, 48, 20, 72, 96, 144, and 288. That's the possibilities for H, the order of H, to be any of these orders. And that's all, and that's it.